If there's one sauce that sneaks its way into burgers, fries, salads, and sandwiches without making a big fuss, it's mayonnaise. Creamy, smooth, and almost invisible until you taste it, mayo has become one of the most important condiments on the planet. But have you ever stopped mid-bite and asked yourself, how is this silky white spread actually made in giant factories? Well, that's why we decided to come with a crystal clear factory process. Before we step into the bright stainless steel corridors of a modern factories, let's rewind. Mayonnaise wasn't born in a lab. Its roots go back to the 18th century, and like most food legends, there's a bit of drama involved. The most popular story says mayo was invented in 1756 when French forces captured the Spanish port of Mahon on the island of Minorca. The French chef, working under Duc de Richelieu, supposedly whipped up a sauce of egg yolk and oil to celebrate victory, naming it Mayonnaise after the port. Fast forward to the 20th century. Homemade mayo was delicious but inconsistent. Whisking yolks and oil together by hand often led to separation. One wrong move and the mixture split. With industrialization came machines that could do this delicate job with perfect precision. Let's approach that one. Factories are obsessed with consistency. Every truckload of sunflower seeds that arrives for ultimately making oil, it is tested in labs before being accepted. Buyers check moisture, foreign material bits of stem and hull, test weight, and sometimes oil content. High oil content earns premiums. High trash content gets deductions. Refining gives it the neutral flavor, clear color, and frying stability that buyers expect. At its core, mayonnaise is an emulsion, oil and water mixed into a creamy spread. The secret glue holding it together is lecithin, a natural emulsifier found in egg yolks. Without it, oil and vinegar would just split like a bad breakup. That's why eggs aren't just an ingredient, they're the foundation. When you're making mayonnaise for millions of jars, cracking eggs like we do at home isn't practical or safe. Factories need eggs that are consistent, pasteurized, and free from bacteria. For mayonnaise, factories don't need the whole shell egg. What they really want is the liquid yolk, sometimes combined with white depending on the recipe. That means eggs are collected, sorted, and often shipped directly to breaking plants, special facilities designed to crack thousands of eggs per hour without human hands ever touching the shells. Now comes the trickiest part, getting oil and water to mix. Normally they hate each other. Pour vinegar into oil at home, and you'll see the layers separate instantly. This is where egg yolk proteins come to the rescue. They act like tiny bridges, linking water and oil molecules so they stay suspended together in a smooth, creamy blend. Factories achieve this with high shear mixers, industrial machines that spin blades at thousands of revolutions per minute. These mixers break oil into microscopic droplets which get coated with egg proteins. Once stabilized, the emulsion becomes thick and glossy. Once the emulsion is stable, vinegar, lemon juice, salt, sugar, and other flavorings are added. Add them too early and they could destabilize the mixture. Add them too late and they won't blend evenly. Factories use precision pumps to add ingredients in exact amounts. Some plants even have computerized recipes stored in digital systems. One wrong setting could produce a batch that tastes completely different. Scientists discovered that mayo is actually one of the most sound-absorbing foods. If you dunk a microphone in it, definitely not recommended at home, it muffles sound better than many foams used in recording studios. That's how dense the emulsion is. Samples are constantly pulled for lab testing. They check texture, pH, viscosity, and even run shelf life simulations. Once approved, the mayo is ready to meet its container. Modern factories run fully automated filling lines where hundreds of jars or squeeze bottles pass under nozzles every minute. Each nozzle pumps the exact amount of mayo, cutting off cleanly to avoid drips. Unlike ketchup, mayo is more delicate because it contains eggs. Factories rely on acidity and careful formulation to keep it safe. The pH is adjusted so bacteria can't grow. Some premium brands also pasteurize the final product by heating it slightly after bottling. This extends shelf life without changing the flavor. Others use cold chain distribution for fresher taste. On average, a factory-sealed mayo bottle lasts 3 to 6 months on the shelf. Open it at home though, and the clock starts ticking faster. The containers then move along conveyors to capping machines, where lids are screwed on and sealed airtight. Labels are applied with barcodes and batch numbers so every jar can be traced back to the specific ingredients used. So, there you have it. What started as a victory sauce for French nobility has turned into one of the most mass-produced condiments in the world. Behind every spoonful of mayo in your sandwich lies a perfectly engineered process. Massive oil tanks, pasteurized egg yolks, high-shear mixers, homogenizers, sterile filling lines, and armies of lab technicians making sure each jar tastes just right. The level of cleanliness is astonishing. Workers wear full protective clothing, and air inside the factory is filtered to minimize contamination. In many plants, visitors must walk through sanitizing foot baths before entering. The next time you casually dip fries into mayo or spread it on bread, remember, you're eating the result of centuries of history, a dash of chemistry, and some of the most advanced food machinery on Earth. Every summer, billions of mangoes make their way from humid orchards to supermarket shelves and juice cartons worldwide. But when the fruit is this delicious, no one would go in the dirt just to see how it's been happening in the industries for centuries. Literally, no one. But you know what? You don't need to go in the muddy fields, just stay with us and we will show you how those delicious mango juice bottles come into existence. Can't promise the hygiene part if that's really what you would have thought about your mango juice. So, the journey starts with carefully chosen grafts. Unlike wild mangoes that sprout from seeds and can take up to 8 years to bear fruit, commercial farms rely on grafted saplings, hybrids created by joining a hardy rootstock with a high-yield branch. This method isn't just for speed, it ensures that the taste, color, and size of the fruit remain consistent across the entire plantation. The ideal mango climate: hot, dry days and mild nights. Mango trees thrive in tropical and subtropical regions like Thailand and Mexico. In these zones, temperatures hover between 25 degrees Celsius to 35 degrees Celsius, and rainfall arrives just in time for flowering. Interestingly, mango trees detest soggy roots. That's why farmers often plant them on slightly raised mounds or gentle slopes, allowing rainwater to drain naturally. Farmers keep a close watch because harvesting too early can ruin flavor, while waiting too long risks bruising or bird attacks. The mango's ability to grow for decades is legendary. A well-cared-for tree can produce fruit for over 100 years, and its yield actually increases after the first decade. By early May, it's harvest time. Farmers look for subtle cues: the fruit's skin color, the swelling of the shoulders near the stem, and the distinctive fruity aroma that signals perfect ripeness. Once grading is complete, the fruits go through weighing and registration. Each crate gets a label indicating orchard origin, variety, harvest date, and maturity level. The washing stage looks deceptively simple, but is one of the most crucial. Mangoes are dumped into large stainless steel tanks filled with gently circulating water. The water temperature is carefully maintained around 45 degrees Celsius in some cases to remove field dust, latex sap, and surface contaminants. These are the mangoes that end up in fruit baskets, premium supermarkets, or exported across oceans to places where tropical sunlight can't reach. Before a single mango moves ahead, the factory's quality control team measures 3 vital parameters: bricks level, firmness, and surface quality. Sometimes those perfectly ripe mangoes might have a tiny blemish, a softer side, or simply be too ripe to survive long travel. Instead of being discarded, they're given a second life: chopped, frozen, and sent out as mango chunks that will brighten desserts, smoothies, and ice creams all year round. The incoming mangoes arrive from the ripening chambers, vibrant and aromatic. Workers check for any signs of over-ripeness or spoilage. Industrial-scale factories deploy rotary mango peelers, machines that use soft rubber rollers and high-pressure water jets to slip the skin off without damaging the pulp. Once peeled, the fruit is split in half to remove the stone, a job that's surprisingly technical. After destoning, the juicy halves move to the cubing conveyors. Stainless steel blades or grid slicers cut the mango into precise cubes depending on the buyer's requirement. Laser sensors continuously check cube size and reject any uneven or crushed pieces. To prevent the cubes from sticking, a thin mist of chilled water sprays over them as they travel down the belt. While the frozen section focuses on locking in freshness, the puree line is where the mango's essence gets intensified. Its aroma, sweetness, and color condensed into a silky golden pulp that will later flavor ice creams, yogurts, and juices. The pulp is pumped through tubular pasteurizers where it's rapidly heated to around 90 to 95 degrees Celsius for 15 to 30 seconds. This short, controlled heat exposure destroys enzymes and microorganisms without damaging the fruit's color or taste. You won't believe what I just heard. They say, grow your own vegetables because you never know if the store-bought vegetables have received the drainage water all along to nourish this faster. First, it's gross. Second, we know nothing. So come with me and let's find out if that's really true. The story begins with a seed no bigger than a sesame grain, pale, flat, and almost unremarkable. Yet inside that tiny speck lies a genetic roadmap that determines everything from how spicy or sweet the pepper will be, to how thick its skin grows, to the exact shade of red it'll turn under the sun. All red peppers are actually green peppers at first. They're the same fruit, just at different stages of ripeness. The green pepper is the immature version. It turns yellow, orange, and then finally red as it ripens. That red color isn't just pretty, it's a sign of transformation. As the chlorophyll breaks down, sugars rise, and antioxidants like lycopene and capsanthin flood in, giving it that signature hue and sweet flavor. The Netherlands, with its limited land and cool climate, manages to grow tons of red peppers using high-tech hydroponic greenhouses systems where plants don't even touch soil. Now, peppers are greedy feeders. Their nutritional demand changes as they grow. Early stages need nitrogen for leaf development, mid-stage calls for potassium to boost fruiting, and late stage demands calcium for firmness and color intensity. Once they're cut from the stem, their internal sugar and pigment development stops completely. Farmers look for an 80 to 100% color change, meaning the fruit has transitioned fully from green to red with a uniform shine. Brix meters, those handheld refractometers you might have seen, are used to measure sweetness. A good red bell pepper should register a Brix value of around 7 to 9, signaling the right sugar level. The peppers tumble gently through rotating drums, rinsed multiple times. After washing, they pass under air knives, high-speed air blowers that remove excess moisture. In modern plants, grading is done by machines that can inspect up to 20 peppers per second using cameras and sensors. They analyze size, color, and surface defects. Based on data, robotic arms or pneumatic air puffs direct each pepper into its assigned chute. Grade A peppers often go to fresh packaging lines. Grade B and C are diverted for steamed, roasted, or diced processing. Before steaming, many factories perform a temperature shock step. Peppers are briefly submerged in cold water around 5 degrees Celsius to firm the skin and lock in color. It's one of the most fascinating transformations in the world of pepper processing, a method that combines chemistry and engineering. At first glance, boiling peppers might seem easier. Dump them in hot water, wait a few minutes, done. But there's a problem: boiling leaches away almost everything valuable in the pepper. Vitamin C, for instance, is extremely heat-sensitive and water-soluble. When peppers are boiled, up to 60% of that vitamin C disappears into the water. Steaming, on the other hand, cooks the peppers with moisture around them, not through them. There's no water contact, no leaching, and the temperature can be precisely controlled. The result? The skin loosens just enough to peel away easily, while the inner flesh softens without collapsing. The natural sugars caramelize ever so slightly, enhancing sweetness, while nutrients remain intact. First comes de-stemming and coring. High-speed rotary cutters slice off the stem caps while a cylindrical vacuum tool scoops out the seed core. The remaining cavity is flushed with water jets to ensure no seeds remain, because even a few stray seeds can create bitterness during storage. Typical steaming temperature, around 95 to 98 degrees Celsius depending on pepper thickness. Duration varies too. Small strips may need just 2 to 3 minutes, while thicker halves can take up to 8 minutes. Lotus didn't come from a multinational food lab like many other foods. It came from a family kitchen in Limbekke, a village in East Flanders, Belgium. And that's what we want to show you today. The year was 1932. The Boon brothers were bakers, running a modest business. Belgium already had a tradition of spiced cookies, speculoos, tied to St. Nicholas Day celebrations. Those were dark, heavily spiced, and usually pressed into wooden molds. The Boone brothers wanted something different, lighter, more delicate. Something you could eat every day, not just once a year. Their experiments landed on a thin biscuit, caramelized at the edges, fragrant but not overwhelming. It was crunchy but not hard, sweet but balanced. Locals noticed. The cookie was perfect with a cup of coffee. It didn't need frosting or filling. The flavor was already complete. Lotus never shouts about its spice blend. You won't see big cinnamon sticks or clove buds plastered across the packaging. Yet every bite carries those notes, subtle, balanced, unmistakable. Once the sheet is ready, it meets the rotary cutter. As the dough passes underneath, the cutter does two things at once. The outer ring stamps the cookie outline, separating each piece. The inner emboss presses the Lotus border and logo. It's branding. Yes, but it's also function. That raised border acts like a frame, strengthening the cookie edges so they don't break in packs. What looks decorative is actually structural. Dough at this point is soft enough to take detail, but firm enough to hold it. Factories track dough temperature carefully for this reason. Too warm, and the emboss blurs. Too cold, and it cracks. Operators know immediately by looking at the logo if the line is running right. The belts themselves are designed for this stage. Dough travels on a smooth belt, but just before cutting, anti-stick treatments prevent sticking. Some plants use flour dusters, others a fine mist of oil. Every measure is about efficiency. You don't want dough sticking to cutters or logos coming out faint. Even if a single cookie got stuck onto the cutters, the entire batch will be a mess. Can you imagine? In warm seasons, dough sheets faster but softens too quickly. In winter, it stiffens and may crack. Factories control ambient climate with HVAC systems, keeping dough rooms within tight limits. That way the emboss looks identical in July and in January. Really? You didn't know that before? Let's talk numbers. A single rotary cutter can stamp out tens of thousands of cookies per hour. The line may run 24/7, producing millions per day. Every cookie has the same thickness, the same border, the same word pressed in the center. Well, that's more in order than my entire life. Cookies and crackers now meet the next stage. Not a small oven, not even a single chamber. These are giants, steel tunnels stretching 60 to 100 meters, wide enough to carry rows of cookies by the thousands. The belt is usually a wire mesh, open enough to let hot air flow through, but sturdy enough to keep cookies aligned. Once the dough enters, it will travel for 5 to 8 minutes, passing through carefully controlled zones of heat. The cookies are cool, golden, crisp, stable. Now comes the stage that decides if they survive the next 6 months of shipping, storage, and handling. All of this happens at astonishing speed. A single packaging line can wrap hundreds of packs per minute. That's how organized and well thought a good factory is. You can't underestimate their production. It is running at speeds far beyond our imagination. Every plate of spaghetti begins its journey long before it twirls around a fork. Before it dives into tomato sauce, meets olive oil, or curls up beside basil, it begins as a grain. A simple golden kernel of wheat, grown under endless fields of sunlight. But today you're going to watch how those delicate wheat kernels turn into crispy spaghetti. First, they need to make the batch so you can enjoy these in your favorite restaurants. Durum wheat grows where summers run dry and the sun doesn't blink. Southern Italy, North Dakota, and the Canadian prairies. Farmers pick durum because its endosperm is hard and glassy, vitreous, they call it, and that hardness is the first hint you're not making bread here, you're building pasta. Why does that matter? A hard, high-protein kernel fractures into coarse semolina instead of powdery flour. Semolina holds its shape in the die, locks in a golden color from natural carotenoids, and gives cooked spaghetti bites without turning mushy. You'll hear numbers in this world: protein around the low teens, strong gluten index, low ash, a firm falling number. But no one brags about lab sheets during harvest. They watch the grain head, the kernel moisture, the weather window. The target kernel moisture ranges roughly around the low teens. Too wet, and storage risks mold. Too dry, and you shatter kernels, creating flour you'll only have to sieve out later. By now, you've watched how the factories turn those wheat grains into the needed flour. Now it's all being packaged and transferred to the spaghetti industries. They make sure the package arrives safely and it's all tested again before it meets the other ingredients for the real process. When semolina finally meets water, the pasta line looks deceptively simple: an auger, a chamber, a die, but the physics inside are anything but casual. Factories don't just dump water in, they meter it with precision, often within tenths of a percent of target hydration. For spaghetti, that range hovers between 30 and 32% moisture, dry compared to bread, wet compared to cereal. Why so specific? Because every percent changes how gluten bonds form, how air is trapped, and how cleanly the dough extrudes. The mixer is designed to look unfinished. If you opened it mid-cycle, you wouldn't see a ball of dough like bread bakers expect. You'd see damp granules that look like couscous. This granular dough is intentional. The goal isn't to knead elasticity into a sheet, but to distribute water evenly around each semolina particle without giving starch a chance to swell too fast. Plants don't run tap water without thinking. They control mineral content and hardness. Calcium, magnesium, and pH can shift gluten behavior. That's why some factories treat incoming water, adjusting hardness, filtering impurities, balancing temperature. Most lines also pre-warm or pre-cool water, so hydration happens at a consistent thermal point. If extrusion was birth, drying is survival. Freshly extruded spaghetti looks finished, but it's delicate, like wet reeds that collapse at a touch. With moisture still hovering above 30%, the strands are flexible, sticky, and biologically alive. Left as they are, they'd mold in a day. The drying step must transform them into something shelf-stable, strong, and resilient. But here's the challenge. Water must leave slowly enough that the outer layer doesn't seal and trap moisture inside, yet fast enough that microbes never get a chance. It's a balancing act every plant treats as sacred. This sets the outer surface, stops sticking, and firms the curtain of spaghetti so the rods can move without tangling. Too aggressive, and you get case hardening. The surface dries into a shell while the core stays wet. Later, as moisture migrates outward, the shell cracks and the whole strand weakens. This is why pre-drying rooms are closely monitored. Sensors track humidity, airspeed, and temperature every second. And remember, all this cutting and packing happens after the real test, drying. If the dryer did its job, the spaghetti will be strong, elastic, and long-lasting. If not, cracks show up now. That's why workers say packaging is where pasta tells you the truth about how it was made.